Today, we want to start looking at chapter 13 with vectors and what we're going to need them for. So today is about deciding what we are going to need our vectors for. Vectors are a thing that we're going to use to describe direction. We're also going to use them to describe position as well. We may have seen that in our linear algebra class, where we had one vector plus a parameter times another vector, p plus t times v, to make a line in Rn. And that kind of gets at what we're going to need vectors for. So let's start off with this smaller example. Let's start off with this circle. Radius 3. Apparently I picked 3 today. Now we can find the slope of the line tangent to the circle at a point on the circle. So let's find the slope of the line tangent to the circle at 135 degrees. Oh, sorry. We are sophisticated math students. That's not 135 degrees. That'll be 3 pi over 4 radians. And what I want is the slope of the tangent line, because the slope of the tangent line is a direction that we're trying to describe. So we have a few tools to go about this. First of all, you can notice that I put a circle at the origin and that I picked an angle of 3 pi over 4. This is so that we can know that the slope of the line is equal to 1. Secretly, we know it's 1, but that's secret math knowledge. We have a few ways that we can go about finding this. We could know that slope is dy over dx, and then we can use our equation to calculate dy dx. So let's do that. So since slope is, secretly, and we already know that m is equal to 1 because we know things. But we want to look at all the different ways that we know this. It's not about what we know, it's about how we know it and how many different ways we can know a thing. So one thing we can notice is that we want the slope, and the slope is change in y divided by change in x. So since slope is dy over dx, slope is delta y over delta x. So let's find a derivative. A nice old school Calc 1 style way of doing the problem. Since x and y are combined into one equation, we can use implicit differentiation. We can say the derivative of 2x with respect to x is 2x, sorry, x squared with respect to x is 2x. If I take the derivative of y squared, I write 2y, but that's the derivative with respect to y. So I have to use the chain rule and multiply by the derivative of y with respect to x, which is good. That's what we're looking for. And then we'll take the derivative of the 9 and come up with 0. Now we can solve for dy dx. We'll subtract the 2x and then divide by a 2y. So we'll have minus x over y. Then we'll just have to plug in this point. And the coordinates at this point, they're going to be the same distance, but x is negative and y is positive. So on this line, x is negative, y is positive. So the slope at this point, which I'm just going to name p, is equal to 1, just as we suspected. So emperor style, just as we had foreseen. But we know that this is not the only way that we can describe what's going on here. We can also look at this circle and come up with parametric equations. So we can look at any point on this circle and say that the x coordinate is going to, I made a radius of 3. So 3 cosine theta and 3 sine theta. So I can describe the circle in parametric equations. That is, I can describe x and y. I use theta. I have a trig class, so I'm going to continue to use theta in degrees when I know I'm going to switch halfway between. I'm going to like halfway remember that I'm in calculus and I start using t like down here, and you'll be like, oh, what's t? I'm like, oh, t is what theta became. And then you'll be like, oh, you should tell us that. I'm like, oh, yeah, I should. So each point on this circle is 3 cosine t, 3 sine t. This is our favorite thing to parameterize. And in parametric equations, we can say x as a function of t is 3 cosine t, and y as a function of t is 3 sine t. Now we can calculate the derivatives at each of x and y. We can find dx dt. The derivative of 3 cosine t is negative 3 sine t. And dy dt, the derivative of 3 sine t is 3 cosine t. Oh, I forgot important parts. Let's decide what our parameters are. Let's use the normal ones. T goes from 0 to 2 pi. That'll take us around the circle one time in the counterclockwise direction. So theta, or sorry, t goes from 0 to 2 pi. So we'll go once around the circle in the clockwise direction, starting at 3, 0. So now what we can do is we can calculate the slope by looking at dy over dx. And I can just divide dy dt by dx dt and plug in the value of t that we're interested in. So our slope is still dy over dx. And if I divide dy dt by dx dt, that'll give us the dy dx that we're looking for. So I just take the 3 cosine of t and divide by negative 3 sine t. Then I just have to evaluate this at t equals 3 pi over 4. Just as we had calculated in the previous problem. But moreover, What we want to do is think about this as a direction. We want to look at the dx dt and the dy dt as a direction from that point, rather than just a slope. The slope pulls out a lot of information. It just says how y is changing with respect to x, regardless, and it doesn't have any regard for direction. But when we parameterize this curve, we introduced a direction counterclockwise. We're going around the circle counterclockwise, starting off at 3, 0. So we started off at 3, 0, and we started going around the circle this way. So when we got to this point, the dx dt and the dy dt show us what direction things are going at that point. So not just a speedometer about how fast we're going, it's going to indicate a direction of travel. So once we introduce direction around the circle, the velocity is going to indicate, broken into parts like this, is going to indicate direction. And we're going to want to describe that with a vector. So here's our circle. We know that if we start off at 3, 0, if we use this as a start point, when t is equal to 0, we're at the point 3, 0. And we're going clockwise around the circle. Sorry, counterclockwise around the circle. We now have more information because we've assigned an orientation to this curve. We've given it a direction. It's not just a circle sitting there where we draw a tangent line. We're now going counterclockwise around the circle, because counterclockwise is the positive direction. We start off at the positive x-axis and go towards the first quadrant first. So theta is equal to t equals 0 here, and we start counting around counterclockwise because we want to head towards the first quadrant first. So when we get to this point, when t is equal to 3/4 of pi, the tangent line is not just some generic line. We have direction. So if we're running around the circle and this is the point where we leave the track, we know that the direction that we're going, we'll describe that with x and y coordinates. We want to use a vector to describe the direction at that point. Any questions? So the slope of the line tangent to the circle at that point is 1. And if I just drew a line here without any kind of direction, we can see that the slope is going to be 1. But now that we've parameterized the curve, we have a direction as we travel this path around the circle. So we have everything is headed in a particular direction. So we can describe how x is changing at that point. So dx dt when t is equal to 3 pi over 4 will be -3 times the sine of 3 pi over 4 or -3 root 2 over 3 root 2 over 2. This is how things are changing in the x direction. It makes sense that we got a negative number because we are clear in the horizontal direction, we're clearly going in the negative direction because we're going to the left. We should also expect a negative for dy dt because at this point, our vertical direction is down. And we can calculate that. So dy dt when t is 3 pi over 4 will be 3 times the cosine of 3 pi over 4. So that'll be 3 times -3 times the square root of 2 over 2. In the first problem, sine of 3 pi over 4 was positive root 2 over 2 because we're in the second quadrant, sine is positive there. And in dy dt, cosine of 3 pi over 4 is going to be negative root 2 over 2. So that's where this negative comes from. So we're describing a direction that things are headed at that point. Questions? We're going counterclockwise because that is the default positive direction when you're when you're dealing with circles. So when you're defining angles in terms thinking in terms of polar coordinate, when you're measuring angles, counterclockwise is the positive direction. We start off at the positive x-axis when t is equal to 0, and counterclockwise is positive because we want to head to the first quadrant first. Otherwise, we'd head to the fourth quadrant first, and that would be weird. You got to lead with Enterprise, not Voyager. All right. So here, sine didn't become negative. Sine is positive. The negative comes from dx dt is -3 sine of t. So sine of 3 pi over 4 is positive root 2 over 2, but multiplied by -3 is going to give us -3 times root 2 over 2. So, and also the sine didn't become negative. We took the derivative of cosine and got negative sine. The derivative of cosine of t is negative sine of t. So what we know is that we can take a path, a one-dimensional curve in two-dimensional space, and instead of describing it with a function or an equation, we can describe it, we can parameterize it. So remember how we describe things. So what we're doing is describing a one-dimensional curve in R2. We can do this with a function sometimes. Y is a function of x. Or maybe x is a function of y. Should probably do this more often leading up to calculus, but all we have to do is turn things 90 degrees. So maybe we don't. With an equation, like we just did, x squared plus y squared equals 9. Maybe we can do an equation Maybe this equation can be turned into a function, maybe it can't. Maybe that's why we need the equation. We can also describe a one-dimensional curve in R2 by parameterizing things. By describing the x and y coordinates separately as a function of some parameter. In all three cases, we want to be able to describe the slope of a line tangent to the curve at some point. And for that, we use derivatives in all the different ways. In this last one, when we parameterize things, we said that the direction at any point on the curve is given by the vector x prime at t, y prime at t. Now, there's a lot of different ways that we could write vectors to distinguish them from intervals and points. Sometimes we write them horizontally with these pointy brackets. To do the classical linear algebra style, I would write them vertically. Another common way to do this would be to use unit vectors. So I'll say x prime of t I hat plus y prime of t j hat, where I and j are unit vectors. I hat is the vector 1, 0, or we could say that I hat is the vector 1, 0, and j hat is the vector 0, 1. That's how we can describe direction at any point on the curve. We want to use a vector to do this when things are parameterized, because once we parameterize a curve, we also assign some kind of direction to the curve. We got to put a little arrow on there. When we're just using a function or an equation, we don't have any sense of direction. We're just kind of like looking at the top-down view, and the path on Google Maps is highlighted in blue. There's no arrow. You're just supposed to know which direction you're headed. So in these first two, we describe direction as m, and we just use change in y divided by change in x. So this raises a question. Why are we looking at this now? All your functions today have been functions of one variable or an equation in two variables. You've been describing one-dimensional curves in R2. So we can see where this is headed since I described these as one-dimensional curves in R2. And since this is multivariable calculus, we're going to want to increase that to R3. When we write a function of two variables, we're describing a two-dimensional surface in R3. But that's not the only thing that we can describe in R3. So when we have a function of two variables, a function of two variables is describing a two-dimensional surface in R3. So if I write this function, got three variables, z equals f of x, y. Now I'm describing a surface in R3. Then if we think back to the section on level surfaces, if we write an equation where a function of x, y, and z is equal to some constant, we're describing a surface in R3. In particular, when we looked at these functions of three variables equal some constant, that's how we describe level surfaces of three-dimensional solids in R4, where w would be like this variable over here. Those two things represent surfaces in R3. But we might not want to describe an entire surface in R3. For example, if there's a fly buzzing around the room, that fly is not, the path of that fly is not describing a two-dimensional surface in R3. A fly buzzing around the room is describing a one-dimensional curve in R3. So our object can be one less dimension than the entire space, or two less dimensions than the entire space if we have enough room. So a fly buzzing around the room describes a one-dimensional curve in R3. So a fly buzzing around the room is going to describe a one-dimensional curve in R3. And for this, we parameterize. We describe the x, y, and we try to parameterize. We describe the x, y, and z axis, z point coordinates. I knew the word was there somewhere. The x, y, and z coordinates independently corresponding to some parameter. Sorry, buddy. I had to reset my mind, so I had to pound on the table, and then you thought someone was knocking at the door, so you kind of had to woof. But it didn't sound like a door knock, so you only kind of woofed. Good job, buddy. I woke my dog up. That's okay. We're going to go right back into calculus, and he'll go right back to sleep because he thinks it's boring. I think a lot of you agree with my dog. So when we describe a fly buzzing around the room, we can describe a one-dimensional curve in R3. And to do that, we'll just define the x, y, and z coordinates separately. So we parameterize. But instead of just x and y, we identify the x coordinates, the y coordinates, and the z coordinates. Excuse me. And we're still making them a function of t on some interval. Now we just have to, now at any point on that curve in R3, we might want to define what direction things are headed. And now we can just do the same thing that we did before. Take derivatives of our three coordinate functions. Where is it? There it is. And make a vector out of it. So here's one of the things that we're going to use vectors for. This is taking vectors and putting it into the context of multivariable calculus. This is why we're going to need to study all this vector business. Any questions? It's supposed to be a K. So I, J, and K are now unit vectors in R3. So I hat is going to be 1, 0, 0. J hat will be 0, 1, 0. And K hat will be 0, 0, 1. We'll use a nice standard basis for R3 because it's easiest to work with in most situations. That's why it's the standard. Questions? So, an important thing to realize. So the way we determine direction is to look at the vector. So when we write a vector is describing a direction, how much in the X direction we're going, how much in the Y direction we're going, and how much in the Z direction we're going. So if we're, say, traveling like we were in our previous example, where at this point, it looks like we're traveling south and west. If I just do, so I'm traveling south and west, I'm doing a negative in the X direction and a negative in the Y direction. We're just describing a direction with vector components. So if this was in R3, and this is the point where we start taking off in our flying cars, then we'll be going, and we're going up as well. Then we'll have a negative X direction, a negative Y direction, and a positive Z direction. Any questions? By the way, flying cars, incredibly bad idea. Look how bad we are at driving cars in 2 dimensions. It's only going to get worse if we have to try to drive the car in 3 dimensions. Yeah, because a crash for positive values of Z is going to lead to 2 crashes. When the 2 cars crash in, flying cars crash into each other, and then when the 2 cars crash into the ground and Z becomes 0. We really need to sort out the self-driving aspect of the cars before we start driving around in 3 dimensions. And I'm talking about like just generic people have a 3D car in their garage. I guess we kind of do have 3D cars because they're called planes, but the only people that get to fly them have lots of training, and there are people on the ground watching all the 3D cars flying around, making sure that they don't crash into each other. There's an entire profession dedicated to people not crashing into each other. So we're gonna need the self-driving thing way before we have the 3D car thing. And before all of this happens, we're going to need to generate energy in a better way than we do right now. But I guess we're working on that. Theoretically, some of you in the room right now, that's going to be your life's work. Producing cleaner energy or finding ways to store the cleanly made energy, which is kind of awesome. So when you're going through chapter 13, there's only 4 sections, and you start doing the homework. This is what I want running in the background. We're trying to describe direction, and we want to be able to describe direction in 3 space. So you want to imagine a fly buzzing around the room, and then at any point at any point in that fly's path, it has a direction, a horizontal direction, or sorry, let's say a left-right direction, a forward-back direction, and an up-down direction. And we want to just break things into those 3 components. We're going from 2 components in a plane to 3 components in space. Once we get the hang of that, we can go to 4 components in 4-dimensional space. And we could parameterize a 1-dimensional curve in R4 and describe that 4-dimensional path. Any questions? Comments? Snide remarks? All right. Tesla's bragging aside, we are also very bad at the self-driving thing right now. So there's that. Any questions? Comments? Deep thoughts? Incidentally, we're probably not going to solve this self-driving thing, because we're still not addressing the fundamental cause of a lot of this, is that we all want to have our own separate conveyance. I mean, I don't want to put global warming on consumers, but we're going to have to get over this. Everybody has their own thing. You know what I mean? Not that anybody's property on my street requires a lawnmower, but if we all had big streets and that there was lawnmowers, why would we all need separate lawnmowers? You know what I mean? Mostly because, and like if they were just like those push lawnmowers where you like go out there and mow the lawn. But I recently took a trip through Georgia, and I was driving along, and I drove by on like one block, like four dudes with riding lawnmowers. Why isn't there just like one for the neighborhood, and they could all like get to know each other and share it, so we don't have to produce 4 of these stupid things? Mostly because, not that these 4 dudes are creating all the pollution in the world, but 4 riding lawnmowers is just, anyway. You know what I mean? I guess we sort of do that because like most of the people on my street just hire someone to come along with a gas-powered leaf blower and clean up the leaves. So we kind of don't all have a leaf blower. So I guess it's progress. We're just paying someone else to do it. You know what I mean? But this whole separate cars thing, it's why there's traffic. So if we get rid of the separate cars thing, and then also getting rid of this going to the office thing, that would alleviate a lot of the traffic problems. Anyway. Any questions? Comments? Deep thoughts? So this path thing and the direction thing is what I want you to be thinking about when you're going through the homework on vectors. That's where things are headed. All right, that's going to do it for today. I will see y'all on tomorrow, and thanks for playing.